Let's take a brief look at the hydrological cycle response. There are lots of details involved again, but I will just highlight the difficulty with understanding or even simulating the hydrologic cycle response. There are all sorts of energy constraints involved, and there are very nice papers written by Miles Allen and Alan Bates and so on. Alan Betts, I think. But I will just highlight some problems here. The general thinking has been that if you warm the atmosphere, obviously temperature warming scales or cooling scales or generally temperature scales are much larger, as we already said. For example, if you are in one town, very likely that most of the nearby towns are going to have similar temperature within, let's say, 100 kilometer, unless there is a front coming or there is a mountain between you, or you are inside and they are on the coast and so on. But it's possible that somebody is seeing snow or rain and you are not in the nearby town, because the scales of rain are very small compared to the scales of temperature. So during the last glacial maximum, the simulated precipitation shows obviously a very different structure than you would expect now. You don't see much of an ITCZ and so on in the precipitation change. So obviously cool continents saw much reduced rainfall, and some places saw colder latitudes saw a little bit less of a reduction in rainfall, and only few regions had no change in rainfall. And because it's a glacial maximum, because the global mean temperatures are very cold, nobody saw increased rainfall in this simulation, right? And this is consistent with what we expect in terms of dryness and increased dust, airborne dust in cold glacial periods. Okay, they will generally have much less global rainfall compared to warmer periods or interglacials. This relates to how much energy is going out to space as well. Cold climates obviously are sending less energy to space, whereas warm climates are sending more energy just by sigma t to the fourth. So the energy balance needed for radiative loss to create global rainfall is going to be different as well from warm to cold climates overall. So how is the hydrologic cycle responding to global warming? This is not a very easy question. In general, there is evidence, clear evidence that extreme events are increasing. So we already saw one plot where the amount of heavy rain has increased by several percent over places and during times when heavy rains tend to happen naturally. So when it rains, it's raining heavily, especially in monsoon regions, for example. Okay, but the point here is, if you look at global annual land precipitation anomalies and look at different products, they are not all consistent with each other. This one is here negative, heavily negative, for example, while all of these are positive. And you can see the range here also going from positive to negative and so on. So even reconstructing past data is not so easy, even as recent as the 1980s and so on. Because if you have rain gauges, it's a rain gauge that's measuring here is measuring very local rainfall and doesn't know what's happening over there. So this is a big problem. And if you look at the global map of trend in annual precipitation from 1901 to 2005 for various regions, you see the same issue, that there are times when different products just don't agree with each other. Okay, so this is something we have to keep in mind. We have general principles which say what should happen to the hydrologic cycle, that it should speed up with warmer temperatures, but the spatial variability of that sped up hydrologic cycle is not as easy to interpret as possible. For example, one study shows that land warming over India does not correspond to local extreme rainfall. Kind of intuitively makes sense because warming the land can produce instability in terms of the, let's say, vertical moist static energy profile. If you don't know what that means, it just means that when you have these instabilities in the vertical, rainfall tends to happen. There are other measures like convectively available potential energy. So basically it's a way of converting locked up potential energy into rainfall. And land warming may produce instability demanding moisture, but moisture has to come from the oceans far away, so local warming need not correspond to local heavy rainfall. Okay, so I'm just making a very heuristic hand-wavy argument, but you can imagine that the behavior on the ocean and on land for rainfall response to warming is going to be potentially very different, because ocean has infinite moisture supply when it warms, whereas land doesn't. And additionally, we don't have much ocean data other than at islands, so we have to struggle with whatever data we have on land. Okay, so that's the story of the hydrologic cycle. But this map here is doing its best to construct various things from 1951 to 2010. So here is R95P, which means the annual amount of precipitation from days with greater than 95th percentile rainfall. So you take a rainfall distribution and you look at rainfall in the top 95th percentile, and you look at the annual amounts received on those days, and you can see that there are many regions where R95P is increased and there are places where it has decreased. So there are complicated patterns over India, for example. SD2 is daily precipitation intensity. So again, various blotchy. The plus marks here refer to statistical significance. Okay, so CDD, frequency of the annual maximum number of consecutive dry days, number of days it doesn't rain. So you can see that there are decreasing trend in some decade in some places, and increasing consecutive dry days in some other regions. Okay, and this is high intensity, so it's trends in normalized units in hydroclimatic intensity. It's a multiplicative measure of a length of a dry spell and precipitation intensity. Nonetheless, the story is that hydrologic cycle generally is intensified, but you can also think of it as in terms of increased floods, and over India it's even increased widespread floods, but also increased droughts in terms of intensity. Okay, so you always have to think about frequency, duration, and intensity. So all those things are being affected by the warming. So this is a critical issue that obviously needs to be understood better. And models have some issues in doing rainfall because, as we said, rainfall processes go from molecular scale, evaporation, cloud, nuclei formation, and clouds, and then rainfall, droplets, impacts of aerosols, and so on and so forth. So models are getting better and better, and there are various details that we won't get into, but precipitation and hydrologic cycles do have some typology of responses that we understand, but there are many things that we don't understand.